I should erase this.
So next up we'll have Patrick Massot from Université, who will be talking about formalized math for the mathematician.
Yes, thank you very much. Thanks for the invitation. I actually have no idea who I'm talking to, so I hope this talk will still be interesting to you. So I'm a mathematician using formalized mathematics, and I want to explain today what we are doing in formalized mathematics and how I hope that artificial intelligence could help us doing mathematics and especially formalized mathematics. So let's see if this works. Yeah, so there are three parts. First, I want to explain what it looks like to do formalized mathematics, because I don't know if everybody is really comfortable with this. I mean, if you're really into machine learning but not so much into formalized mathematics, I hope you'll be able to understand what it looks like. And then I will very briefly, because this is not the main focus of this talk, explain why mathematicians could care about formalized mathematics. And then I will somehow come to the topic of the conference, which is how artificial intelligence could help. So this will be all about dreaming what artificial intelligence could do for us. So it's maybe a bit early for a Christmas list, but this is anyway what I'm going to have at the end of the talk. So there are several software you can use to do formalized mathematics. The examples I will show use Lean, which is a software developed mostly by Leo Demura at Microsoft Research, but everything I will say could apply just as well to other proof assistants such as Coq or Isabelle or even MetaMath, I guess, and others. So in order to show what it looks like to do formalized mathematics, I need a proof to explain to computers. So it's all about explaining proofs, definitions, and proofs to computers. And so I will use the examples that I always use with mathematicians. I hope it's elementary enough, but it's not very important if you don't get all the details of this proof. So the proof I will explain is the Heine-Cantor theorem. So it says that if you've got two metric spaces, and the first one is compact, then any continuous function between those spaces is uniformly continuous. So you could think, I mean, x could be simply the unit interval, unit segment in real numbers, and y could be real numbers if this is not elementary enough. So I have only one slide to prove this theorem. So I will cheat and use basically a big theorem to deduce it without too much work, and I will use the extreme value theorem. So remember, the goal is to prove that for all positive epsilon, there exists a positive delta, so that whenever x and x primes are at distance less than delta, then their images f of x and f of x primes are at distance less than epsilon. This is what I need to prove, so I fix positive epsilon. And then I need an idea, as Jordi explained. You need an idea, and the idea in this proof is to look at this set K. It's a set of P in the product x times x, so that the distance between f of P1, the first component of P, and f of P2 is more than epsilon, or no less than epsilon. And I said that this set K is closed because the function f is assumed to be continuous and the distance function is continuous. And more or less it's a closed set in a compact metric space, so it's actually compact. And now the extreme value theorem gives me a P which minimizes the distance function on this compact set. So for all other Q in K, the distance between P1 and P2, so remember P is a pair of elements of capital X, is less than distance between Q1 and Q2. And I said that the delta I was looking for, so I was looking for some delta because I have fixed epsilon positive, I need to prove there exists delta positive such that. So I use delta is distance between P1 and P2. So I need to prove that for all x and x prime, the distance if the distance between x and x prime is less than delta, then the distance between their images is less than epsilon. So I fix x and x prime in capital X. And the goal, which is not this implication, if you contrapose this goal, you get exactly the definition of P, the property that P minimizes distance. So this is the proof I want to formalize. So I will now switch to using a proof assistant, so in this case, Lean. So the first thing we can do already with a bit of help from artificial intelligence is to formalize the statement. So this is the informal statement is here. That x and y be metric spaces, assume x is compact, any continuous map from x to y is uniformly continuous. So now let's open a chat with OpenAI Codex. So this is the interface built by Azerbayev and Ers to OpenAI Codex. With a prompt, so OpenAI Codex was trained on all of internet, and then they added a prompt with, I don't know, maybe at most 50 lines of lean code to put this transformer model into a lean mood. And so let's put that as my statement. Just send it to the API over the internet, and it's thinking about it for a while. I hope not too long. Come on. I hope I'm connected to the internet. Yeah? Okay, so it gives me something. So just copy paste this, or I guess I could click this copy icon, and let's see, no. Let's see if Lean likes this statement. It says unknown identifier, so maybe I need to write bigger. Unknown identifier, uniformly continuous. So here I'm a bit stuck. So it likes the beginning of the statement, but not this uniformly continuous, because in the mathematical library we have been using, we somehow save two letters by removing this ly, and this is now no longer an unknown identifier. So this is now a formalized statement. So let's see what it wrote. So it says you have metric spaces, x and y, and x is a compact space, f is a function from x to y, and I have this assumption hf that f is continuous, and then I need to prove that f is uniformly continuous. So that's not too bad as auto-formalization, but still if I don't know that uniformly continuous should be spelled uniform continuous, I'm a bit stuck. But let's count this as a success of artificial intelligence. So now, what about the proof? Yeah, the function name was not given. So now I'm trying, because I think this was very good first success, I just copy paste the informal proof. And then I've got red everywhere. Okay. So and so far we can't do much better than just commenting out those things. And try to actually write a proof without using artificial intelligence. So let's say I want to say the goal is this for all epsilon, etc. So I happen to know that I need to rewrite. So RW means rewrite. I won't explain everything, but it just transformed the goal into what we wanted. So look at the right-hand side of the screen. Is showing what is called in Lean the tactic state. So this is the state of the proof, current state of the proof. You've got all the casting, all the things that were fixed. So x and y, just think that type means set. So x and y are sets, and x is a metric space, y is a metric space. I've got all my assumption. And the funny symbol here, which looks like a T, which has fallen on its side, it means current goal. I mean, you need to prove this. Okay, and then you need to, I won't explain every command in detail, but you need to give instruction to the computer. So the fix positive epsilon is spelled intro epsilon, and then I give a name epsilon post to this assumption. And you can see the goal state has updated. Now epsilon is fixed, and I have this assumption epsilon post saying that epsilon is positive. And then I need the idea. So let's set this k to be the set of p in x times x, such that distance between f of p1 and f of p2 is more than epsilon. So it's almost the same syntax as in my informal proof. And now I start proving stuff by asserting intermediate statement. So I say K closed, which is the claim that K is closed. So now I've got two goals. And the first goal is to prove that K is closed. And then the second goal, in the second goal, I will have this extra assumption. I will return to my original goal, but with this extra assumption that K is closed. So now I'm asking for a suggestion from the computer. And it suggests a lot of things. For instance, that one, it doesn't cost anything. The first one, it suggests to prove that the complement of K is open, which is like the definition of being closed. So that one is not risky. The second one is really risky. It says, hey, it's sufficient to prove that K is finite. But okay, this is sufficient, but there is no reason why K should be finite. So let's skip that suggestion and just look for something that sounds reasonable, and that one is good. Refine is closed LE, so it has something to do with less or equal being closed. And now I've got three goals. I need to prove that the constant function sending p to epsilon is continuous, and the right-hand side, the function that I mentioned in the informal proof, f and distance are continuous. So I can just ask the computer to deal with those continuity proofs automatically. And I've got my fact that K is closed. And now I want to make progress. I claim that K is compact. And I'm asking for suggestion from the computer.
This is not AI, right?
No, this suggestion, I will discuss that, of course, at the end of the talk. But I mean, it depends what you call AI. I mean, this is computer thinking instead of me thinking. So you can say this is AI, but it's nothing like neural network or anything. The computer is just trying every lemma that it knows about and try to apply it to the current situation. And here it finds an exact match. So indeed, K is compact. And now let's use the extreme value theorem to obtain such a point P. So let's do that. I want to obtain P with properties P in and H, saying that there exists P, etc. So the statement that I announced. And I ask for suggestions about proving that. And this is a tough one. There are lots of suggestions that are completely useless, but I'm looking for suggestion using compactness of K, and I think the only mention of compactness of K in this list of suggestions is that one. So let's try that one. K compact that exists for all LE. I now have three goals. And the first one is a bit worrying. The first one is prove that K is non-empty. Where was this in my informal proof? Because I'm using the extreme value theorem whose conclusion is giving me a point P in K. So if K is empty, this is not very likely to happen. I mean, if you think, we are an audience of people working in artificial intelligence, so we got tricked by the mathematician into believing a false proof. I've given this false proof to many mathematicians, including Fields medalists, without anyone complaining about proving that K is not empty. So maybe K is non-empty. What do you think? Why is K non-empty? X could be empty. That would be pretty bad.
But it's still true.
And the theorem is still true. Yeah, but I mean, what if F is constant? Then, so K is the set of pairs of points that are sent at distance at least epsilon far apart. So if F is constant, then clearly K is empty. So we have a proof of uniform continuity of continuous function on compact metric space that simply fails for constant function, which is a bit sad. Okay, so let's fix that. I will just split depending on whether K is empty or not. So I have this cases command, which gives me two goals. One goal where I assume that K is empty, and another goal where I assume K is non-empty. And I also put the proof in the k empty case. So in the case where k is empty, then any delta will do. So I say use 1, and then there is a 3 lines long proof saying that 1 works in that case. So now I'm back on track because I now have this assumption that k is non-empty that was required by the lemma. And by the way, if I ask for suggestion now, I think this suggestion will be ranked much higher than previously because I now have, you see, now this is the first suggestion of from Lean because now it has this assumption H saying that k is non-empty. Okay, and then I have again some continuity stuff to prove, so let's do that automatically. If I can type continuity, no, why how do you, I will start over. Continue, and use autocomplete. Okay, and now I can go to the next line, which was use distance between P1 and P2 as my delta. And I need to fix x and x prime, so I know how to do that. This is intro x, x prime. Oh, Lin complains there is nothing to introduce. Ah, because I've got actually a conjunction to prove. I also need to prove that delta is positive. So what was the proof again? There was no proof that delta is positive. Why is delta positive? Yeah? You had a suggestion? So here's what I said to my students. One quick check you can do about your proofs is did you use the assumptions? So you see, at the very beginning of the proof, I fix epsilon a positive real number, and presumably the fact that epsilon is positive is somewhat important. And where did I use positivity of epsilon in my informal proof? Nowhere. So now is probably the right time to use that epsilon is positive. So I will do that now, and this is 5 more lines to write, and now I can introduce h and h prime, and I think I missed my copy-paste of the end of the proof. I was meant to contrapose and use the assumption. So contrapose.
Petra, can you scroll down a bit? You cannot see the...
You cannot see? That's weird. Is it better now? Yeah. Okay, so let's contrapose, and then this is exactly capital H applied to something. And now, what is it? X prime? Is it happy now? Yeah. So this is what mathematics formalization looks like in a like semi-realistic example. Of course, I've chosen this example so that it doesn't go too bad, but still I was able to prove something with some help from the computer and also some help to find gaps in the proof and some help to find proofs of intermediate statements. So now, how am I doing on time? Okay, good. So what kind of math can you do using this? I mean, we will have more information in Kevin's talk, I think, but we already know that computers like this, without using much artificial intelligence, except for the auto-formalization that I used in the very beginning when I asked Codex about the statement. So it can handle very long proofs. So for instance, the Fade-Thompson odd-order theorem was formalized in the proof assistant Coq by the team of Georges Gontier and Assia Mahboubi and many other people. So this is a proof that is, the original paper is 250 pages or something like this, and the detailed proof is like 2 small books of mathematics. So this can be done. We can also tell the computer about very sophisticated objects, such as perfectoid spaces, which are gadgets invented by Scholze. So in that case, it's not a very long proof, it's a very sophisticated object where you need to prove many lemmas in order to simply write a definition. So this we can do, so we did with Kevin Bezard who is here and Johan Comlin a few years ago. People often ask me whether this is only good for logic and algebra and combinatorics and things that are very close to foundations or combinatorics. Very recently with Floris van Doorn, who is sitting in the back row, and Oliver Nash, we checked that the computers can do differential topology and things that are rather visual and counterintuitive. So if you've seen videos on YouTube of sphere inversion or Smale sphere inversion theorem, we've checked that this is actually valid very recently. So you can do geometric stuff. And you can also explain proofs that have not yet been really digested by the community. Because if you look at Fate Thompson, I mean, they explained the theorem of Fate and Thompson like, I guess, 40 years after the proof. And the proof had been digested and written in textbook forms with simplifications and more details, and which is, I mean, this is already an amazing project that they managed to formalize this, but this was very much a digested proof. And in the case of the liquid tensor experiment that I guess Kevin will tell us about, it was really brand new mathematics, and the author, who knows what he says when he talks about mathematics, Peter Scholze, was not fully sure that it was correct, and it was not digested by the community at all. Nobody except for the author understood the proof, and still we managed to explain it to computers. So a team led by Johan Komlin and Adam Topas managed to just explain this by fighting one lemma after the other until they proved this complicated theorem. So this is a extremely quick overview of where we stand. You can also have a look at what has been formalized in different proof assistants. For instance, in Lean, it's pretty easy to do. I don't know if I have a web browser somewhere. But if you go on the website of the community of users of Lean, so you type just Lean, Lean Prover community, there is an overview of the library that you find easily, and you can see stuff that has been formalized. I mean, you can see stuff about periodic numbers, you can see stuff about, I don't know, permutation groups, you can see homological algebra, chain complexes, just reading random bits, linear algebra, topology, and I mean, you can have a look at what is known. So there is a lot of elementary mathematics, and then some, in some specific areas, very advanced mathematics. So what is it good for? So first, it's really fun. I mean, you saw it during the demo, I hope, that it's really fun to use those proof assistants. Of course, it's also frustrating when the computer is not collaborating the way it should, but it's a lot of fun. I mean, it's pretty striking. I've been doing mathematics for quite a long time before getting interested in formalized mathematics, and I never saw conferences where every talk mentioned having fun before I started going to formalized mathematics conferences. And I don't know, people were happy. I'm doing symplectic topology originally, and I know people seem pretty happy to do symplectic topology, but I've never heard someone starting a talk in symplectic topology, but I will go to explain how much fun I had proving this and I don't know, this video game experience, I mean, although the graphics are a bit sober, it really works. Okay, then I will give some more details about how it can be used for checking, explaining, teaching, and creating. So checking is, as you've seen, I detected a gap in this proof that I found on Wikipedia originally, and so you can hope when you're a referee from mathematics papers that your only job is to read the introduction and decide whether the statement is relevant and interesting, and whether there are new ideas that are hopefully explained in the introduction and not somewhere buried in the proof, and then just let the computer check the proof. Okay, so this is complete science fiction, but it's okay. This is an AI conference, so I can. So there's no short-term hope, but we can have, I mean, focused targets. We could hope to check carefully small numbers of very big proofs that are too big to fit in a human mind, like I mean, of course, the most famous example will be the classification of finite simple groups, just 10,000 pages of proof that is too big to fit in anyone's memory. And we could do that, but we would need a lot of help from artificial intelligence to do it in a reasonable time scale. Or we would need an army of people working on this. This also a kind of artificial intelligence. We could focus on very technical fragments, I mean short but extremely technical, like in the liquid tensor experiment, and Kevin will talk about that. And that already works, so this is not science fiction. We can already choose so in the case of the liquid tensor experiment, I guess it's like 20 pages that are extremely technical but and difficult to check, and we did that. Yeah, I mean, this is also, so this was so the theorem Kevin is talking about is a theorem that was checked in proof assistance before it was accepted by a journal, and I don't think it's accepted yet. So it was a, yeah. So the author is still waiting for a referee report, but he already checked using a proof assistant that the proof is correct. So I don't know what the journal is doing. Yeah, it was a pretty fancy result that was in analytic number theory that was checked before it was accepted. And I don't know what the journal is doing now. Just they didn't realize that. Okay, they have principles. They shouldn't accept the paper before 2 years. Yeah? Okay. So checking is good. But especially at the current rate, I mean, the current speed of formalizing mathematics, it's not so useful, at least yet. For me, the most compelling reasons to do formalized mathematics is to help explaining stuff to humans. So I want to have a new kind of document. So this is also mostly science fiction, but it should come rather soon. I want a new kind of document where the readers can choose the level of detail. And I don't mean seeing every detail all the time. I want that the reader is given like a normal mathematics document, but any word, any sentence where you want more details, you can ask for more detail. So let's take a stupid example. In my proof, in the beginning, I had distances everywhere. So let's see, for instance, in the definition of K, in the goal here. I've got distance between A and B less than delta implies distance between f of A and f of B less than epsilon. And let's say I'm completely confused. I don't know which distance we are talking about. Is it the distance in the source space or the target space? And it was not written in my informal account. And it's also not written here, except that if the computer is happy with this proof, it means that somehow that information was inferred. And I can just ask, I mean, for instance, this distance function, I click on it, and I see this is the distance function on x. I mean, and this says this is a real number, this distance between A and B, and this is the distance function on x. And if I want to know where this distance function comes, I can also ask, and if I click on that one, I see this is the distance function on y. And okay, this is not a super convenient interface to have to go to the proof assistant and ask for details like this, but I mean, all the information is there. So for me, this is the main goal. I want to be able to zoom in and out of a proof and see more details and maybe change my mind and because I'm frightened by details and just zoom out again and so on. Now, very quickly about teaching. I've been using this proof assistant Lean for teaching for a number of years, and more people are using proof assistants for teaching mathematics. This is the new part. I mean, people in computer science departments have been using proof assistants for teaching either logic or discrete math or principle of programming languages forever, but in math department it's pretty new and it works really great. I don't have time to expand on this, but and the goal, the only relevant point is that the goal is not to have students that are experts in using a proof assistant. The goal is that they are experts at writing traditional proof on paper, but they use proof assistant as an intermediate tool to get that expertise. And now for creation of mathematics. So when you use a proof assistance, it's very easy to change the definition and tweak everything, the definition, the statement, and the assumptions and everything, and see what breaks. I mean, in a normal life, when you write a paper and halfway through the paper you decide that maybe you need to change the first definition of the paper slightly, it's really painful because you need to go over all the lemmas from the paper and see what is still correct, what needs to be adjusted, and this is complicated, and usually either people don't bother or they do it, but they half do it, and then the paper becomes inconsistent, but not too badly inconsistent, so a reader will fix it. But with a proof assistant, you can just change the definition and see, within seconds or maybe minutes if you have a big project, what is broken and what is still working. You can also find unnecessary assumption. I've did that when we were doing perfectoid spaces. It's very nice to read a theorem in a book, especially in a book that is meant to be carefully written, and at the end of the proof, realize that you don't know where you use one of the assumptions. Just delete the assumption, see the computer is still happy, and just you've learned a more powerful theorem. Just because the assumption was there because of a copy-paste mistake, and it was actually unneeded. And there are more sophisticated versions of that. You can ask computers to weaken the assumptions automatically and stuff like that. So more importantly, and I will say more about that later, searching for mathematics should be much easier using formalized mathematics, at least if artificial intelligence can help a bit. And the last remark about creation of mathematics is that formalized mathematics encourages clean abstractions and clear thinking, and not forcing a proof, but really finding the right definition and the right concepts. And I will only do a very quick experiment about this. What if, instead of doing all that, I asked for suggestion at the very beginning? So the suggestion is apply a theorem saying exactly what you want. So this is a full proof. So of course this is still, on paper or on the computer, the most efficient way to prove something is always to refer to some previous proof. So this is not the interesting part. The interesting part is what is the proof that we are talking about. So because we are on a computer, we can just ask to see the proof, and just press one key. And this is the proof that you get, which is from the formalized library. So the proof is this 5-line computation. And this 5-line computation, the notation is rather good, but still let's look at it in LaTeX. This is the proof that was in the library. And you see, it doesn't start with let x and y be metric spaces. It just starts with a more abstract concept. And then there is an algebraic computation involving concepts that were not at all present in my proof. So uniform structures, filters of neighborhood, some algebraic operation of pushing forward and supremum of filters. And I won't have time to explain any of this, but the proof, which is mostly the proof taken from Bourbaki, is just much more efficient than what I was doing, and using much more abstract machinery. And of course, it's also cheating in a sense that the first line calls all the content of the theorem. So if this is the analog of calling the extreme value theorem is this first line, and then it's all easy. Okay, so now I think I'm halfway through my talk. Is that correct? I'm confused because I didn't start. 20 minutes here, okay, so that's perfect. So now this is the Christmas list time. So what could artificial intelligence do for us? And I should say right away that the answer is not, I think I should just type the statement of the Riemann hypothesis and just wait for the computer to give me a proof with nice explanations. If it can do that, then okay, that's nice, but I don't think that's an interesting topic to discuss because, if it can do that, then I don't know, it can do anything. So we will be living in a very different world. So let's try to just keep slightly in touch with reality in this Christmas list. so we saw in my demo that Lynn was suggesting lemmas to apply, but I had to go through the list of suggestions and choose one of the suggestions. And each time there were many suggestions, at least 10, and if I just start to explore the tree without any pruning or any optimization, then I mean, it explodes immediately. So clearly we need something to replace what I was doing, just going through the list and saying this looks promising, this looks stupid, or something like this. So I hope this is very much doable, and this does not necessarily go through a neural network or stuff like this. And there are other proof assistants, especially Isabelle has a stronger form of automation than the software I was using for the demo, and using, I guess, more classical, I don't know if we can call this AI. Can we call this AI? But I mean, things like Sledgehammer or stuff like this, is it? Okay, maybe recent versions are already using a bit of machine learning, but they are, I mean, clearly using SMT solver and stuff like that. So I don't know if SMT solver counts as artificial intelligence. I'll let that question to you. Okay, but still, we can work in this direction. You can work in this direction. And then there is the next level would be to suggest ideas, like Jordi was saying in his talk. And in the case of my proof, the idea is this definition of the capital K, the set that I introduced out of nowhere. That is really the idea. If you look at this, so I need to go back to the original proof. I mean, the idea in this case is clearly this line where I set K equals this thing. So this could have been, I don't know, generated by a transformer or something, and then this idea with the idea of applying this theorem, the extreme value theorem, which is this line. Okay, the two ideas are introducing this set and applying the extreme value theorem. Okay, and of course, there were also these stupid part of the proof. You can see this is the part where I treat the case where K is empty. I mean, it's a completely stupid case, but it's still 4 lines long in my final proof. And so clearly we don't want to see that. I mean, this has been generated by a copy and paste during my demo, but it was not generated by artificial intelligence. It was generated because before the talk, I just put that in my copy-paste buffer. It was not, I mean, every time it went fast, it's because I used copy-paste, not artificial intelligence. And the other thing is when I prove that delta is positive, this is also 5 painful lines that should go away for Christmas. Yeah, maybe that could be stronger automation could do that. I skipped something. And then there is the topic of auto-formalization. So auto-formalization means you give a text, a normal mathematical text, and the computer turns it into formal math. So this is what I did with the statement at the very beginning of my demo, and it worked pretty well, except that I was stuck with this uniformly continuous instead of uniform continuous. So it would need ways to recover from such failures. And for instance, so this thing that I've used is available since last summer, and it's very easy to use. You've just had to add an extension to your VS Code editor, and you can play with it right away. But I never used it for actual work. Maybe I should, but I never felt that it would save me time to use this auto-formalization. So maybe it's because I'm old and grumpy, but yeah, I learned the language before this tool was available, and maybe we should ask someone younger, someone who started this summer. But okay, with some improvement and maybe some error recovering capabilities, it could become useful. And for proofs, so that was only about statement. Then there is a bigger dream of just copy-pasting the whole informal proof into the system and hope to get a formal proof. And then there are many difficulties with that. So for instance, you see my informal proof actually had serious gaps. So, I mean, if you are very optimistic, the auto-formalization will include fixing those gaps, but I don't really see how that could be possible. But if you can do that, of course, it's very nice. At least, maybe the auto-formalization could extract the intermediate statements. Like you see in my formalized proof, I have those intermediate statements, have K closed, saying that K is closed, have K compact, and obtain those P such that. I mean, those three intermediate statements, maybe they could be extracted from the informal text and turned into intermediate formal statement without proof. That would be already very useful. So this is about a single proof. And then if you are very optimistic, you can think about auto-formalizing theories. You just take a whole textbook and just put it inside the computer, and the output is I don't know, 100 lean files with everything formalized. And it's much harder, and it's not only much harder because it's more volume, it's much harder because everything needs to be consistent, and the various definitions need to play nicely together. And there are also many technological issues on the proof assistant side that would take much too long to explain. But there are many choices to do when you define stuff in a proof assistant to make it usable. And when we have new people coming to formalize mathematics, we always, when they ask, what can I do? I want to help, because, I don't know, they saw a talk advertising what we are doing with lies, such that this demo suggesting everything is easy. And so they come and they are very enthusiastic and they want to, and they come and they say, I'm working on, I don't know, a representation theory. I want to define a representation theory of such and such algebras. And we always tell them, oh, definition, it's really complicated. You should rather find a lemma that is not proven, but where all the definitions are already there. And it's not because definitions are difficult from a mathematical point of view. It's technically, you need to make a lot of small decisions about how to encode your definition into the proof assistant. And I have no idea how this could work with auto-formalization. But of course, I also have no idea how computers recognize tigers, like we saw in Jordi's talk. So maybe, yeah. Well, but at least I can recognize tigers on photos, and I have a hard time doing formalization. We'll see. And then we can also go in the other direction, do unformalization. And remember, when I explained the motivation for formalized mathematics, I explained that for me, the main motivation is explaining mathematics to human beings. So maybe it would be really nice if we can take a formal proof, which is hard to read. I mean, if you simply look at this proof, I mean, if you give this text to a normal mathematician with no training in reading formal proof code, and the statement is somewhat readable, but the proof isn't, especially if you remove the comments that came from my informal proof. And even with the tactic state evolving from line to line, it's still very difficult. So why not just generating sentences from this? I mean, the problem is that if you do that, you really need the result to be accurate, because otherwise it's a complete waste. I mean, you put all the effort to write a formalized proof, maybe with help from AI, but still, I mean, let's say it was a lot of effort. And then the AI comes and unformalizes it, and it's garbage. And we've tried. I mean, there are experiments have been made just unformalizing statements, formalized statement, and sometimes the result is amazing, and sometimes it's completely garbage, and even worse, sometimes it looks plausible and it's still complete garbage. So, which is of course the worst thing. Okay, that would be great, but I would rather work on doing unformalization with more traditional programming method than artificial intelligence. But still, if you can do that reliably using neural network or any kind of machine learning, that would be useful. But again, I mean, if you want this to be really useful, it needs to include access to information that was implicit in the proof, like this. Is it the distance on x or the distance of y that I showed earlier? Okay, next item on this list, searching. So I already mentioned that. When you are actually using a proof assistant with a sizable library of formalized mathematics, you spend a lot of time searching the library for stuff that have already been defined or already been proven. And of course, it's very easy to just type a statement, a formal statement, and ask the computer, is it already known? You've seen it with the suggest command that I was using. I mean, if the statement is already fully known, it will suggest to use the statement that is already there. But this is not enough, I mean, because there are so many variations on the way you can state anything that it will never be an exact match unless you're very lucky and you've prepared a demo for some talk. So we need some fuzzy search using artificial intelligence. And note that there is a formal version of this, but also an informal version. I mean, maybe we could, you could give as an input to the search a formalized statement or simply a sentence saying, I want to know whether it's already known that continuous function and compact metric spaces are uniformly continuous. And then the computer would both do the auto-formalization and search the library, fuzzy search the library.
That's hard, right?
I don't know, who knows?
I mean, just there's infinitely many primes. Could a computer find that same in our library?
Yeah, I don't know. I mean,
our library, the formalization that there's infinitely many primes is for all n, there exists a p which is prime and bigger than n.
yeah.
There's no mention of the word infinite.
Yeah, exactly. So for instance, this is, so I don't know if people got that. So Kevin gave an example. We saw in Jordi's talk, the very first statement was the set of p natural number such that p is prime is infinite. So you can type this and search for this, but the statement in the library, it does not look like this. It looks like for all n natural number, there exists p such that p is prime and p is bigger than n. Which of course is equivalent, but I mean, it really doesn't look like the first line. And this is indeed what I mean by fuzzy searching. I mean, that's probably a really tough case, but I would be happy already with simply searching. For instance, if there are two conclusions in the theorem, maybe they are listed in a different orders, or maybe the data is packaged in a slightly different way. And when you do formalized mathematics, you need to encode everything into some kind of data structure, and there are many ways to do it. And you could just, and it's extremely frustrating when you're doing formal proof and you spend time just unpacking some data and repacking it slightly differently so that the lemma you want to apply applies. And this is stuff where we need help. We could also ask the computer what it thinks about our statements. So for instance, earlier I said maybe k is non-empty, maybe k could be empty. But I had no way to ask the computer's opinion. So there are stuff that already exist. If you are proving lemmas more on the software engineering and computer science side with finite stuff, for instance, you want to prove a lemma about lists or some operation on list or something like this, there are tools that we just try to find counterexample by exploring finite databases and report whether they found a counterexample. But we don't really have this for topological spaces or metric spaces and functions. So I guess in the case I was describing, you could imagine that the computer will try to prove that k is non-empty using every function between two metric spaces having 3 elements or something like this and find the counterexample. But for other parts of mathematics, there is really no finite counterexample that could be found. It's very interesting to still get an idea of maybe this is wrong. So this is clearly related to the experiment that Jordi was describing in his talk, in finding counterexamples. Except that if you need to train a specific neural network just for this task, then clearly you cannot run this every 2 lines in your proof. I mean, I would want something that every time I claim an intermediate result in my proof, it tells me, I don't think this is true. Okay? Okay, and then let's be even more ambitious. What about actual mathematical creation? So let's say I want to find new analogies and generalize stuff. So for instance, this is the elementary definition of a uniform continuity of a function from real numbers to real numbers that you learn in the first or second year of math study at university. And so we give this definition to the computer and we prove a bunch of lemmas saying that uniformly continuous functions are continuous and some extension by continuity properties. I mean, a bunch of lemmas using that definition, and then ask the computer, what do you think about this definition? And can you somehow magically derive the definition of metric spaces from that? I don't know. But, I mean, at some point, mathematicians did that in history. It's a pretty big jump. I guess there were intermediate points. Probably norm spaces came first, but I'm not even sure. But still, in principle, the question can be asked. I mean, you can just feed this to your transformer or whatever and get as output a new definition saying, I think this notion would be nice to study. Or maybe a common generalization, say I give the definition of uniformly continuous function for metric spaces and topological groups. So the trick is, you see, when you want to generalize this, you can say this absolute value of x prime minus x, I will replace this by distance between x and x prime. But you can also focus on this minus sign and saying, I'm using subtraction here, and I'm using the size of the subtraction. So there is a version of this definition for functions between groups, so they have a subtraction, and equipped with a topology, so with a notion of size. And if you look at those two definitions, it's not clear at all what is the common generalization, but maybe computers could invent uniform spaces. That is the fancy notion, just puts everything in the same framework. And maybe they could generate conjectures too. We haven't seen this in this talk, but in Jordi's talk, there was this number theory conjecture that was somehow generated by artificial intelligence. I mean, at least with hints from artificial intelligence. And of course, there is the question of asking the computer whether a mathematical definition and proof is beautiful, which is very important for reinforcement learning purposes, because we don't want to self-train, the computer self-trains on ugly definitions and proofs. So I have no idea how to do that. What else? In all those questions, I mean, you can start from formalized input or from informal input. It's not completely clear what is the most impossible version and this. And one quick point about teaching. So I mentioned that I'm using Proof Assistant for teaching. So I'm asking students to write proofs to convince the computer, and then they need to write the same proof on paper to convince normal human beings. But of course, when they try to convince the computer, I want the computer to be pedantic, but not too much. I mean, there are justifications, just proof steps that I don't want to see on paper. I want the computer to do it automatically. You've seen that the computer can already do, for instance, all the continuity proofs have been done automatically by the computer in my demo. And by the way, I can ask to see the proof that was found by the computer. This is not an oracle saying, yes, it's continuous. I mean, I can ask to see, maybe I should have shown that. If I, for instance, this first continuity proof, so let me isolate the first one and ask to see what is the proof term that has been found by this continuity tactic. And it would tell me that, so it was proving that a constant function sending p to epsilon is continuous. And what it found is this lemma continuous underscore const So you can ask to see the proof that was found. So the computer can do part of the proof, but the specification for my teaching is I want the computer to do automatically everything that I wouldn't want to see on paper. So you can see this specification is not very actionable. I mean, because there are clearly cases where the computer automation is too powerful and cases where it's not enough powerful. And I don't know, maybe the computer could decide whether or not it should help students. Remember, this is a Christmas list. And then one provocative one to finish the talk. So what about automatic referee report? I mean, currently, when you send a paper to a journal, then the referee gets the paper, and he won't get, or she won't get any credit for doing this hard work of referring the paper. So of course, it's not true that anytime you submit a mathematics paper, every detail will be checked line by line. So what people do, I mean, they check some specific proofs that are very important, but otherwise they assess the relevance of the result and they assess the plausibility of proof. Like they look at the proof, they say this ingredient and this ingredient, okay, those are well-known techniques that can prove this kind of statement, so probably it's okay. And just, no, let's go to the next lemma. And I mean, we can't do anything but that. I mean, it's impossible with the time we have, and so maybe we could just automate this. It's just going from informal paper to informal referee report without using a proof assistant or anything. Maybe that would be more accurate, I don't know. So this is the summary. So I've listed many artificial intelligence targets related to my demo. So I've put all of them here except for the last one, which is not really serious. But for me, as a mathematician and a user of proof assistant and formalized mathematics, the really important one is, I mean, fill in easy proofs, because this is really annoying when you need to stop and start providing details for something stupid. And filling in difficult proofs, I don't care. I mean, if I'm explaining something to the computer, I probably already know the idea. So, I mean, it would be nice, but not as useful. And same for the next one. And it's not really clear which ones are emphasized, but the searching is the other one that is emphasized. For me, that would be really the most helpful part would be this fuzzy search in the library part. So if you can prioritize this before Christmas, that would be really nice. I think this is what I wanted to tell you.
All right. Thank you, Patrick, for the great talk. Do we have some questions, comments, suggestions?
When you ask a student to formalize even an easy statement, sometimes they get it really wrong. And so it means that even if they can, and then they can generate even a proof that is wrong because the statement is wrong. The proof becomes easier, but sometimes it's kind of fiddly, and you don't necessarily realize that you're proving something by having false as an hypothesis. Is it possible to mess at larger scale when you do formalization?
Yeah, okay, so that's really purely about a question about formalization. So Stan is asking whether we could simply mess up the statement and prove it, but having achieved nothing. So for instance, in this liquid tensor experiment that Kevin will talk us about, I mean, the goal is to prove that some very fancy abelian group is actually the trivial group, is 0. And this fancy abelian group, it has a very fancy definition, and then the very fancy proof that this group is 0. But what if we messed up the definition and we just define this group to be 0? And then of course, we can convince the computer that this group is 0 by just saying this is true by definition. And in that case, it would be really obvious, but maybe there could be a more subtle issue. And that's very true. I mean, we still need to check the definitions. And in the referee dream that I explained, it was kind of a loophole in this dream is that if I check the introduction and then the computer says the body of the paper is correct, but I don't check the definition that were given to the computer, could be completely wrong. I mean, it's very easy. I could do it in Lean to write theorem Riemann underscore hypothesis 0 equals 0, and then give a proof and try to claim my $1 million, but that probably wouldn't work. So yes, indeed, we need to be careful with that. There are ways to at least make this less likely by just proving properties of the easy properties of the definition we have written. And so there is an interesting blog post about that on the blog of the community of Lean users. If you go there, there is a full blog post on definition in a liquid tensor experiment, which explains what was done in that particular case to make sure that the definitions were sensible. But yeah, it's still maybe the only place where you can still get flows and, from in the process. I hope it's fine. I mean, it's certainly, I mean, much less plausible than having a flow in the original proof. But you cannot reach 100% certainty as long as, I mean, yeah, definitions entered by humans are still part of the system. And definition entered by human with help from the computer. So as you've seen, the computer fills in a lot of implicit information. So we saw the example of the distance function. I just write distance between A and B, and the computer sees that A is an element of capital X, so probably this is the distance in X, so it should go and find some metric space structure on X, and it does a lot of background work like this to make sure you can type definitions in a way that is still readable and concise enough. But of course, it also means there is more room for misinterpretation from the computer. But really, the only protection we have against this is actually using the definition to prove lots of easy stuff, and maybe try to prove wrong stuff and fail, and then we can use those definitions to prove difficult stuff and be confident that the definitions are okay. Yes? Yeah.
Which domains in mathematics do you feel are the hardest to formalize in Lean, or the least formalized so far, and why?
So I've explained in the beginning, I mean, it's clearly easier to formalize very algebraic stuff. And this is why I've started this sphere eversion project, which is about flexibility in geometry and very geometric and visual stuff. So yeah, I mean, algebra is still easier, but you can do geometry and analysis. And so far, we haven't found anything that resisted formalization. And every time we think, oh, this will be really tough, and we manage it somehow. But it's still, I mean, the fraction of mathematics that has been formalized is completely ridiculous. I mean, if you compare to everything that exists in mathematics, the part that has been formalized is simply not visible at all. I mean, we've made forays into very advanced directions just for proof of concept purposes, but the global landscape is that nothing is formalized. For the research level mathematics. Of course, if you stick to undergrad mathematics, then almost everything is here, especially if you are ready to switch from one software to the other, depending on which branch of mathematics you're interested in. So yes, I don't know what else I can say? I mean, what is complicated is when there are lots of implicit information and implicit identification. It starts already very early in the story. When you define natural number, so depending on your foundations, the definition won't look the same, but let's say you have natural number, and then you build integers, so numbers with signs, and then rational numbers, and then real numbers. But each time you go up one level, this is actually not an inclusion. I mean, there is a map from natural number to real numbers, and it's an injective map, so you can think that a natural number is a real number, and there are many ways to construct real numbers, but in none of those ways you'll get an inclusion of natural number into real numbers. So there are those inclusion maps, they are inserted silently by any modern proof assistant. When the proof assistant expects a real number and you give it a natural number, it will say, okay, I need to silently insert this function, which is an injective function from natural number to real number, and it will try to do it in a non-obtrusive way and just let you not think about it. But the more and more you pile such implicit inclusions or implicit isomorphism between different ways of looking at things, the more complicated it gets. And so this is, for instance, one kind of obstacle. But it never really prevented us, or I mean, when I say us, I really mean in a very general way, the people doing formalized mathematics were never prevented from going somewhere because of those issues. But it can be more or less pleasant. So my hope is there is no obstruction to formalizing anything except for time. I mean, it's still very time consuming, and this is why we need.
And the false.
Oh yeah, okay. The false stuff is also an abstraction to be formalized. Yeah, but no, we need the software to be easier to use and with more automation, so either coming from artificial intelligence or for more traditional software engineering. But we will take over the world at some point. I don't know when yet.
Is there any other question? Okay. All right. Sorry. Yeah. Okay. Sure.
Okay. So I just proved that. So you are a traditional mathematician as well, right?
Oh yes.
So how does it affect your usual life as a mathematician? Do you do in your area of specialization the proofs directly in formal way, or you still have the separation between paper and pencil and?
So recently I've been doing mostly formalized mathematics, not fully. I'm still doing a bit of traditional math, but the bit of traditional math that I'm doing is currently not formalized. It's just too far away.
Do you understand the statements of the questions you're working on?
Yeah, I mean, it depends. I mean, the problem is, in order to even state something, you need so many definitions and constructions, and we are really far away from having libraries of formalized mathematics where you can just pick a random pure mathematics paper and formalize even the statement. So this is the main obstacle. It's not that those mathematics are unformalizable. I hope they are, but there are way too many prerequisites. I mean, I work in a rather high-tech part of mathematics in symplectic topology, and there are a lot of foundational things that are not there yet. But I hope that at some point before I die, I will just join my two paths, but it won't be next year.
Hi, I wonder if the way you teach computer to formalize math follows the way human brain discovered math since Euclid, and do you start like that by axiom and then you build?
No,
bigger and bigger?
I'm really, so there are many different styles of using a proof assistant for teaching. The one I've been using for 4 years is really, I'm working on stuff that the students learned in the previous term. So typically in a first analysis course with sequences of real numbers, convergent sequences of real numbers, continuous function from real numbers to real numbers. And I want the students to reprove lemmas from this area. So for instance, my students reprove that if you've got two sequences of real numbers that are convergent sequences, then their sum is also convergent and it converges to the sum of the limits, stuff like this. And culminating in things like the intermediate value theorem or the extreme value theorem, but not the general case for uniform spaces. I mean, the extreme value theorem for function on a segment of real numbers. And I give students all the definitions and the statements already. They don't have, in my classes, they don't have to state anything, or except for intermediate statement, like they have that I used in my demo. But the lemma statements are already there, and the definitions are already there, and I just ask them to fill in proofs. And so it's, I don't really ask them to be creative. I mean, the only difference between what I've shown and what they do is that I'm not using the same interface as what we saw, because so in the beginning I used that, all the commands that we saw, intro, RW, refine and stuff like this, and it worked fine on the computer, but then when they tried to write proofs on paper, they had a very hard time translating those computer proofs into paper proofs. So I switched to using commands that are in a controlled natural language, so that they look like, maybe we could just have a very quick look at what it looks like. Probably. So that would be the English version. So for instance, that would be an example of a statement. So this is proving that if you've got a convergent sequence, u goes to x0, and f is continuous at x0, then the sequence f compose u goes to f of x0. And you see it starts with, let's prove that something, fix epsilon positive by hf, the assumption applied to epsilon, using epsilon post, we obtain s, and so on. So this is validly in code. So this is understood by the computer. And, but this is, of course, this is harder to write than the regular lean code, because there is this cognitive dissonance between the thing that looks like natural language, but actually has extremely rigid syntax. I mean, just as rigid as a normal programming syntax. But then when they manage, so they find it a bit harder to write like this, but then once this is written, it's much easier to go on paper and write a pen and paper proof starting from this. But otherwise, this is what I'm doing with students is what you've seen in the demo. Oh, of course, I don't tell them about suggest. This is a secret.
And one more. Are you currently working with an AI researcher to improve your field with AI, or?
No, not directly. No, myself, I'm not working with. I mean, there are people, as we saw, using Lean for an AI, but I'm not directly involved in. I mean, if anyone wants to give me one of my Christmas list items, and I'd be happy to help in any way I could. I mean, I don't know anything about machine learning. I mean, I've read like popular science accounts of machine learning, maybe slightly more, but not really. No. But that would be interesting.
And maybe if I may, to answer your question, like, so some of us are working to do just that, and you will hear a lot more about that this afternoon.
Yeah, sure.
Any other?
Yeah, maybe during this afternoon and tomorrow we'll learn that everything on that list is actually already done.
Yeah.
That would be nice.
Not quite. All right, if there are no more questions, let's thank the speaker again. So there is a buffet in the hall that you can go to. We will start again at 2:30. Thank you.